Okay, and in this time we're going to talk about damp harmonic motion. As we have seen in class, simple harmonic motion can be described as, for example, in this case, we have a spring with an object, and if we apply a force here, the object is going to move to the front and to the back, But as the system is frictionless, it is not going to stop at any point or any moment, right? So, for example, in those cases, the movement is a little bit like ideal because we're not considering the air or the friction of the material or the surface or something like that. But in this case, the damp harmonic motion is considering the friction. So we have our normal formula of the simple harmonic motion, that is the amplitude times the sine or cosine times omega times t plus a phase constant, that is phi, right? In this case, the damp harmonic motion is going to describe a movement a little bit different. We have three different kinds of damp harmonic motion. The first one is little damping. It is not like just considering small velocities for the movement, and it could be described in this way. The position in terms of time can be defined as a constant b times an exponential to the minus omega of gamma times t sine of the angular frequency prime times the time plus a c constant times an exponential to the minus omega gamma time times the cosine of the angular frequency prime times the time. Right, and we have two conditions for this part of the little damping. The first one is that the omega gamma has to be equal to a constant b, that is the constant of the damped motion, over 2 times the mass. And the other is that the omega prime is going to be equal to the square root of the initial angular frequency to the square minus the angular frequency of gamma square. From this formula, these two formulas, we can get this other one. No, this other one, that is the initial angular frequency is going to be equal to the square root of the k over n. Right, this is our other formula. And in this movement, b is going to be little, so it's going to be less than 2 times the square root of m times k. Then we have another type of damped motion, that is the big damping. It's a little bit more complex. We can have the x in terms of the time. It's going to be almost the same as in this one, but the power that it is going to have is a little bit more complex because we are getting this formula inside the power, also in this term. B is defined as 1/2 of the initial position minus this term of here, and the big damping is its characteristic is that B is going to be bigger than 2 times the square root of m times k. In the other part, we have the critic damping, that is going to be not less nor bigger. It is going to be equal to, we don't have it here, B is going to be equal to 2 times the square root of m times k. And it's a movement a little bit easier, and we just have b times the exponential to the angular frequency of of gamma times time plus time. This is another variant of this equation. We're going to consider time to be a multiplication of the constant and the exponential. These are the terms that make that this condition happens. And this is about damped harmonic motion. We can also write this part of here, the little damping that we're considering. We can also write it as the formula that we have seen in class, that is A times an exponential 2 minus the angular frequency times time. This angular frequency is defined as B over 2m. So we can also rewrite it as minus B over 2m times T times the cosine of omega prime times time plus a phase constant. We can also express it in this way. Okay, why I draw Newton's here? Because I'm interested in his second law. The sum of all the forces is going to be equal to the mass times the acceleration. We're going to have two forces acting in this part of here. We're going to have the force of the spring minus the force of the spring, because the force is going to be opposed to the movement that is taking place in the spring, minus the F, the damped force, that is this one, and this is going to be equal to our mass times our acceleration. Right? The force of the spring, we know it as minus K times X. This part of here is going to be minus B times B, the velocity, and this is going to be equal to mass times A. In Newton's terms, we can rewrite this. We can pass this part to the other side, and then we will have m times the second derivative of x plus the b plus the first derivative of x plus the constant of the spring times x, and this is going to be equal to 0. Right? So this describes also the damped oscillation because of the resistance that is applying this constant of here. And I'm going to explain the loss of energy in damping oscillations. I'm just going to stay with everything. This is Kuko, that is understanding everything. And this is Beppo, that is a little bit lost in the theme. Right, so the next step is going to define our change of energy with respect of the time. This is going to be equal to the derivative of u with respect of time plus the derivative of our kinetic energy. And okay, this is going to be equal to the derivative of u of our potential energy in the spring is going to be 1/2 of the constant of the spring times x squared over dt, plus the derivative of the kinetic energy, that is 1/2 of the mass times velocity squared over dt. Right? So if we answer this, it's going to be k times x dx over dt plus m times b db dt. Right? So the next step is going to, okay, we know that is equal to kx. I'm going to invert the terms. Equal to m times the velocity. We know that the velocity is a derivative of the position with respect of the time times dv. dv, we know that is the, oh, let's put a dv plus the constant times x and the derivative of the x dt. We can take out this factor and divide this part of k to take also that factor, and it's going to be m dx dt. The derivative of the velocity, we know that is the acceleration, and is also the second derivative. The second derivative of the position with respect of the time, and plus k over m x, right? We have this other part, and from this formula that we got here at the beginning, we can take this part to the other side. So we will have then m. I will express this in terms of Leibniz notation. It is going to be this. I'm going to pass this to the other side. So plus and I'm going to divide all by m. So this is wrong. This m is not going to be here. Just the acceleration. So we have this plus, because I'm going to divide everything by m. So this is going to be over m, and this b was originally b over m. So this is the original equation. I'm sorry for that. And we can also express this as gamma, because gamma is b over m, and k over m is going to be our angular frequency squared. Well, so this is the same expression, but in Leibniz notation, it's going to be the same times b over m, b over m, the first derivative of x, plus omega squared times x. And I'm going to pass this term to the other side. This is equal to 0, so I can express also this as equal to minus b over m dx dt. Right? But as we said, bm was equal to k over m, so we can also replace this part of here by b, right? Bx. And as we can see, k over m was, sorry, our angular frequency squared. So as we can see, this term of here, of this side of the equation, is going to be the same as this part of here. So we can then take just this and replace it for this. So we can rewrite this as m dx dt times our minus b over m dx dt. Right? And as we can see here, this m is going to be cancelled out, and then we just got this minus b times d squared dt squared.